Welcome back to Multigrid Methods. We're talking about the finite element method in this chapter, chapter 6, and we want to see the application of the multigrid method for solving problems derived by approximating PDE using the finite element method, and we want to fill in all the details for this method. Uh, the difference between what we're doing now and what we did in chapter 3 is that in this chapter 6, we're going to be completely general with the mesh structures that we're going to introduce. We're no longer going to require that our meshes are necessarily one-dimensional. They could be two-dimensional. They could be for a domain that is not a square, that's not that might be complicated, might not be a very simple shape. This, some of the theory which I'll mention can also be extended into 3D, although we won't be exhibiting any examples in 3D. And of course, it's hard to draw examples in 3D. But the theory will abstract to that level. Last time we were talking about these nested families of finite element spaces. We started by creating what are called triangulations, sort of a base or primordial triangulation, and then refining these triangulations through bisection or quadrisection in the case of 2D. Basically, I think the thing that you can keep in your mind is this example here. We just keep creating finer and finer levels of this mesh as we go up. So the lowest level here is sometimes called the basement or the root level, level 0, and then the first level is stacked on top of that. And then, of course, you keep going up in level from there. So that we create this hierarchy of these nested triangulations. And remember, the main thing we said about these triangulations is that they should be conforming, that there should be no hanging nodes. We described the finite element spaces defined subordinate to these triangulations, and those were called V sub L. And the finite element spaces that we're going to use are quite simple. They're globally continuous functions that are polynomials of degree 1, so linear polynomials on each triangle. So that's our standard definition or the standard notation. We say K for triangle, not sure why, but that's become standard in the finite element literature. The K, each triangle in the triangulation, such that we want to have the boundary conditions vanish. Or in other words, the trace on the boundary, the point values on the boundary should be 0. Here's an example of a primordial mesh, level 0 mesh that we're going to refine through quadrisection. So each triangle gets quadrisected into 4 subtriangles, or each parent gives 4 children. Okay, so that parent gives those 4, this parent gives these 4, and so on. You always quadrisect by connecting the midpoints of edges. So there's 3, each triangle has 3 edges and 3 midpoints, and so you just take those and you connect them up, and that's how you get your child triangles from the parent. So this is the level 0 mesh, this is the level 1 mesh. Now, interior vertices are going to be very important for us. If you look at this level 0 mesh, there are only 2 interior vertices, and these are labeled in this with these black dots. But as we go up and become finer, go up in level, we get more black dots, of course, as you would expect. So here we start off with 2 and we end up with 13. If we do another refinement, roughly speaking, we're going to increase this number by something like 4 times every time we do we go up in a level, roughly speaking. So as I said, those interior nodes are very important for us because we're going to use those to create bases. Now, I should have pointed out, when we define our finite element spaces, we're doing something which is kind of very basic here. We're using piecewise linear finite element spaces. We could use piecewise quadratic, that would be P2, or piecewise cubic, P3. And if you've taken a finite element course, why don't you raise your hand electronically or otherwise if you've taken the finite element course here at UT before. Let me see a show of hands for those of you who have taken that finite element course. if you haven't taken it yet, then I will be offering that again in the next fall. So just keep lookout for that. So a couple of you have taken the finite element course, and what we cover in there is what happens when we increase the order here. So instead of being piecewise linear, suppose we make this piecewise quadratic or cubic. What we find is that we'll get an increased convergence. Now we can still do all of our finite element space work and all of our multigrid work if we have P2 functions or P3, etc. But everything simplifies quite a bit if we just have P1. So that's what I'm sticking to here. So um, that I say that all to say that for the piecewise linear case, all we need to keep track of really is the number of interior vertices that we see here. So an interior vertex is where a triangle has a corner. Okay, multiple triangles have a corner, but it's not on the edge. It has to be in the interior. Okay, so you just look where the triangles have or meet, where they have corners, and those give rise to the interior vertices. So those are going to be important for this next definition. Suppose that VL and TL are defined as above. So our finite element space is defined from our triangulation as defined above. Suppose that NLJ J equals 1 to NL is the set of interior vertices for the triangulation TL. So notice that this NL, this number you've seen before, that's going to be a number that we use to designate or characterize the size of the level L space, the dimension of the level L space, if you will. Let BL denote the Lagrange nodal basis for VL. That is, BL is equal to the set of all of these functions, and I'm going to describe those in a second. They're the same number of functions NL as there are nodes interior vertices in the triangulation. Sometimes I'll call these nodes, and that's why it's given this letter N. The interior vertices are interior nodes. So there's the same number of basis functions as there are vertices or nodes. So each VLI in this set is from the space VL. So this means piecewise linear, globally continuous. And it's the unique function with the following property. Evaluated, so psi Li evaluated at NLJ is equal to the Kronecker delta symbol. It's going to be 1 whenever I and j are equal to each other, and it's going to be 0 otherwise. So these functions are called hat functions. We've already seen what these things look like in one dimension. And the analogy to two dimensions is quite similar. And these, in two dimensions, I really do think these things look like hat functions. And so that's why they're called hat functions and why they're called sometimes the hat function basis. We're always going to assume that our mesh has at least one interior node. Okay. Now you can create a mesh that doesn't have one interior node. Let me give you a silly example. So suppose I have this triangulation. All right. It has two triangles in this triangulation, but no interior nodes. So I could remedy that by just making another cut, and that's going to give me the interior node that I want. Okay, so we're gonna always assume that we have one interior node to start with. Otherwise, it's a triviality. So here's what these hat basis functions look like, or chapeau functions. So suppose that we have this mesh, and we have two interior nodes. So this was that primordial mesh that we mentioned earlier. I'm gonna I'll oscillate between calling these nodes and vertices, but they're the same thing. So let's consider the function which is 1 at this node and 0 on all other nodes. Well, there's only one other node in this triangulation. And remember, every hat function has to belong to the finite element space. That's a requirement. So that means it has to be 0 on the boundary. And by the way, sometimes these are also called tent functions for obvious reasons. But this function here is 0 on the boundaries. Notice that, sorry, that was a little off. There's my boundary. It's 0 out here. Now, I'm defining this function to be a function in the space. That means it has to be globally continuous. It's going to be 1 at this node, and it's 0 all other nodes, and it's 0 on the boundary. So this defines a function which looks like this tent, for lack of a better word. Now, it's non-zero precisely on this set of triangles. 1, 2, 3, 4, 5 triangles. And these triangles give us what's called the support of the function. But what about off of that support? Say, what's the value on these triangles? Well, the value on these triangles is just 0, because remember, this function has to be a function that's globally continuous. It has to be defined everywhere on this mesh. And it's defined by the fact that it's 1 at this node and 0 at all others. But that just means it's going to be 0 out here. All right, so that's one hat function, one chapeau function, one tent function. And of course, I think you can see what this function, this hat function looks like, the one that's going to be 1 at this node and 0 on all other nodes. Here's another example. This one is using a nice regular uniform mesh that's gotten by. So by the way, this is drawn in projection here. So this is like the x-axis, and this is like the y-axis here. So this should be the mesh of a square, but it's drawn in projection so that you can see what this thing looks like. So I probably should emphasize that. So it's actually the mesh of a square, or the grid over a square. Okay, so just so you're not confused. And suppose, let's consider this node here. What's the hat function look like with respect to that node? So it has to be 1 at this node and 0 at all others, and it has to be 0 on the boundary. And it has to be otherwise piecewise linear. So we don't have to specify any more information. All we have to say is what node is it? Is it 1? And on what nodes is it 0? Well, actually really only have to say on what node is it 1. It's going to be 0 on all other nodes. So this is the function. This is the correct function. All right, so the following is easily established and left as an exercise for you. And this is easy to prove in one space dimension. It's a little bit harder to prove in two space dimensions and higher, but if you find the trick, it's not so bad. So suppose that we have constructed our finite element space subordinate to our nested triangulations, as above. And suppose that BL is that basis defined in 3. So where the NL is the number of interior vertices. Then BL is a bona fide basis of VL. So it really is a basis. We started off by calling it the Lagrange nodal basis for VL. That's a little bit of a premature definition because we don't know if it is actually a basis, but it turns out with this result, this proposition, that it actually is a basis. Okay, so what's next? So from that, we can show that if our, remember, our triangulations are nested. So from the 0 triangulation, we get to the next triangulation by quadrisection, and then so on and so on. So suppose that VL and TL are constructed in that way. Well, then the finite element spaces that we've defined subordinate to these triangulations form a nested family of subspaces. So V1 is going to be a subspace of V2. I should say here, there's no reason to leave out V0. So V0 also is in this chain. Okay. They're a nested family of subspaces, so that each one at the lower level is a subspace of the one at the finer level. That means functions at the coarse level, or at a relative coarse level V1, will be included in V2, but not vice versa. So functions that are in V2 may or may not be in V1. So they are proper subspaces in the sense that there are functions in V2 which are certainly not in V1. All of them are subspaces of this infinite dimensional Hilbert space called H01, which I defined earlier. It's a space of weakly differentiable L2 functions that have a zero boundary trace. That's H1 or H01. This is a Hilbert space and it's infinite dimensional, whereas each one of these are finite dimensional. In fact, what we can show by knowing the size of the bases is that the dimension of each one of these spaces is exactly the number of interior vertices, NL. Furthermore, it's easy enough to see that NL has this sort of nested structure because we're adding nodes to create the next finer level. N1 has to be strictly bigger than N0, which is strictly less than N2, and so on, all the way up to the finest level. Our finest level is always designated by a capital L. That's always the case. Capital L designates our finest level. And just a reminder, NL is precisely the number of interior vertices of the triangulation. We always also have this nested structure for our mesh spacings or mesh sizes. HL minus 1 is always 2 times larger than HL. This is a very simple fact related to the fact that every time we do a refinement of a coarse parent, we get 4 children in 2D. We get 4 children that are congruent to the parent. Okay, so 4 children triangles which are congruent to the original one, which means that they have the same angles, which is easy enough to see. And the edges of each one of these triangles is half the size of the previous edges. At least this one here is half that. This is going to be half of this guy, right? So that's why we have this relationship. And the proof of that is also an exercise, but I think it's easy enough to see. Suppose that BL is the Lagrange nodal basis for VL. Then for every L, there exists unique numbers, what I'm going to call PL minus 1, JI, where J is between 1 and NL, and I is between 1 and NL minus 1 with the following property. So there's a collection of numbers with the following property that satisfies this. Each coarse level Lagrange nodal basis element. So how do I know it's coarse level? It's L minus 1 relative to this fine level basis function at level L. And it's numbered I. How many are there in total? Well, I runs from 1 to NL minus 1. That's how many elements there are in that coarse level basis. Now remember we said that in general, VL minus 1 is a proper subspace of VL. So that means anything that we draw out of this space is also in this space. So this is a function from that space. It happens to be a basis function. And what I want to do is, knowing this, I want to write this as a linear combination of the basis functions from the finer level space. So is it possible to do that? Well, yeah, because this function in this space is also in this space, so it can be expanded in whatever basis we have for this space. Well, we know that BL, because of the previous proposition, is a basis for that space. So we should be able to expand this function in these basis functions psi Lj. J equals 1 to NL. Remember, there are NL of those basis functions. And the coefficients that we get in this linear expansion are the numbers that we're going to call, because we can call them anything we want. We're just going to keep track of them in the following way. We're going to call them PL minus 1 J comma I. All right. So I've already explained why these numbers exist. And here's the here's the proof, which is just going to exactly repeat what I just said. So VL minus 1 is the linear subspace of VL, and BL is a basis for the latter. For every function in BL, well, BL is a subset of functions in VL minus 1, which is a subspace of VL. So there has to exist these coefficients, and we even know that they're unique. Now, the way we number them or whatever we call them is not necessarily unique, but given an I, given an I in that basis, and given whatever L we want, then the expansion in the basis for this space is a unique expansion because we know that all basis representations are unique. So that's it. That's all there is to that. So what we call these guys is kind of irrelevant, but we've numbered them and named them for certain specific reason. These are going to be the elements of our prolongation matrix, as usual. So for L between 0 and capital L inclusive, we're going to define the prolongation matrix. Actually, that's not true. Prolongation matrix is, this is a small typo. It's not defined for 0. So I think I should make this 1 here. Okay. It doesn't work for 0 because that would be the E minus 1 prolongation matrix, and that's nonsensical. So the ijth entry of this matrix is going to be denoted by PL minus 1 I comma j. That's how we get the ijth entry of this matrix. So now I've switched the orders of I and j on you here. Okay. So it was previously L minus 1 j I, where j is the index of the greater number of elements and I is the index of the lesser number of elements. I've switched the order now, as you see, but I've done so in a consistent way. So the number of rows in this matrix, that's this first entry here, that's the size of that index, that index can be. That's the number of rows. Okay, so that guy can be NL in number. So that's why the number of rows corresponds to NL. It's still consistent. And the number of columns corresponds to this number, NL minus 1. So that's why I'm going to use the more standard notation where I use J for the second index and I for the first index. Okay, so this is the prolongation matrix. How do you define a matrix? Well, you define a matrix by telling a person what are the entries of that matrix, but you have to specify every possible entry of that matrix, and that's what we've done here. So we've completely defined the prolongation matrix. Now, is this definition useful in any way, shape, or form? We don't know yet. All right, but before we get there, let's see one of the results of this choice. Suppose that VL minus 1 is an arbitrary function from this finite element space. So remember, we have this concept of a function now in a finite dimensional space, and we have its coordinate representation in the bases. Okay, so we'll get to that in a second. Suppose that VL minus 1, well, this very second, I guess, VL minus 1, boldface, that means vector, is the coordinate vector of VL minus 1 in the Lagrange nodal basis. So I hope everyone gets this understanding. When I have a function, okay, in VL minus 1, and I have a basis for that function or that space, then I have a coordinate vector. And the coordinate vector is just the elements in the representation. So what I mean is we have this function VL minus 1, and that guy is an element of capital VL minus 1. Well, that means that I can represent it in the basis. So let's do J equals 1 to NL minus 1, VL minus 1 J, and time psi L minus 1 j. Now it's this guy which depends on x, and these guys here are just coefficients. So this object here, VL minus 1, is going to be the object, which is a vector that has the following entries. I guess the easy way to write it is this way. The entries of this vector are just going to be VL minus 1j, the jth entry. Okay, the j entry of this vector is this object or this coefficient in this linear combination. So what we call this object here is the coordinate vector. The coordinate vector with respect to the basis. Now, if you change the basis, you change the coordinate representation. Everybody knows this. If you change the basis, you change the coordinate representation. No big surprise there. Suppose that VL, boldface, is the coordinate vector of this same function, but written in this basis. Now, does this make any sense to you? So I hope it does, because look at it this way. VL minus 1 is an element of VL minus 1. So this has the basis, the natural basis, BL minus 1. But this is a subset or subspace of VL, and this has the natural basis BL. So that means this function is also in this space. That means I can write this function in two different basis expansions. I can write it in this basis expansion or this one. Now, which one is the right one? Well, neither is the correct one. They're just different ways of looking at the same function. They have two different basis representations in two different bases. Now, these bases aren't equal to each other by no means, but the fact that this is a subspace of this vector space allows me the fact that I can use this basis to express this function. Now, here's the punchline of this little result. VL, if VL is the coordinate vector of VL minus 1 in the basis BL, then it satisfies that, or it follows that VL is equal to PL minus 1 times VL minus 1. In other words, if I want to find out what this basis representation vector is, okay, this basis coordinate vector, then all I do is I take my prolongation matrix and I'm going to multiply it times the coordinate vector in the basis BL minus 1. That's it. That's what this little lemma says. All right, so let's prove that. As usual, if we want the ith component of boldface VL minus 1, then that's that element there. And if we want the ith element of VL, similar sort of thing. Notice that here there are, because this is the coordinate vector in the basis, or with respect to the basis BL minus 1, there are precisely L minus 1 of these coefficients. And because this is its coordinate vector in the space VL, or with respect to the basis BL, it has NL components in its coordinate representation. All right. So now let's just use what we've defined already. So VL minus 1 can be expressed in the basis of BL minus 1, right? And there are its coordinates. But now we know that each one of these guys can be represented in the basis for VL, namely BL. Sorry that VL and BL are similar sounding words. This can be represented in the basis BL, which is precisely that computation there. These numbers are pre-tabulated, okay? So we have them stored up and they only have to be calculated once. So we call this an offline calculation or a tabulation process. It's a one and done sort of process. Well, now I can, because these are two finite sums, I can rearrange sums at will. I can pull things in, pull things out. So what I'm going to do is I'm going to move this sum on J out front as the first sum and the sum on I interior. And so I'm going to rearrange things to look like this. So this thing in block in the middle, okay, sum from J equals 1 to NL times this basis function psi Lj. So this is just some coordinate which depends on j. What is that new coordinate? Well, this is just matrix vector multiplication. Kind of a complicated way of looking at matrix vector multiplication. But what I'm doing is taking the jth row of this object and multiplying that times this vector. Right? That's exactly equal to the jth component of this product vector, PL minus 1, VL minus 1. But that's exactly what I wanted to show, because whatever appears here are going to be the coordinates of this vector. But now we've switched bases, right? We started out with this course level basis and we switched to a fine level basis. So whatever these coordinates are here are the coordinates in the fine level basis. So these are the coordinates of that vector boldface VL. And so that tells us, so that's what I'm doing there, just replacing that with that fact. That tells us that vector is equal to that product, that matrix vector product. And this all results in the fact that all basis representations are unique. If we're really dealing with a basis, then we're done. Okay. All right. Now we're going to define the restriction matrix as we usually do, because we're really interested in satisfying the Galerkin condition. And to do that, we know that we should probably take the restriction matrix to be equal to the transpose. That's the usual Euclidean transpose of the prolongation matrix. That's how we're going to define things here. We don't have to do this. We'll talk about using a modified restriction matrices when we talk about cell-centered multigrid in the next chapter. But for now, we're just going to follow the usual prescription and use the fact, or use the idea, I guess you could call it the prescription, that the restriction matrix is just a transpose of the prolongation matrix. Okay, suppose that we've defined, just as above, our prolongation and restriction matrices. Then we know that the rank of those matrices has to be exactly equal to NL minus 1. So it's the smaller of the sizes of the number of rows and number of columns. So PL minus 1 has NL rows and L minus 1 columns. Its rank is its number of columns, and vice versa for the restriction matrix. It has NL minus 1 rows, NL columns. Its rank is the smaller of those two. So what we say in this case is that both matrices are of full rank. Both matrices are of full rank. There are two ways to show this. There's a direct way to show it, and then there's an indirect way of showing it. I'll show you both ways. So here's the direct way of showing that. Let's just deal with P, the P matrix. The same sort of ideas can be done for the R matrix. Need a space in here. Mid space. Okay. So let's set this guy, this product, P L minus 1, VL minus 1 equal to 0. So this represents a linear combination of the NL minus 1 columns of PL minus 1. That's because anytime I do matrix times a vector, that's a weighted column sum. So we covered this back in 571, classical numerical analysis. So the idea is anytime I make a product, AX, this can be thought of as a linear combination of the columns. Okay, I hope you all remember that. And of course, the length of this, or the coefficients of this vector act as the coefficients for this linear combination. So that's the same thing here. If I have a vector here from R and L minus 1, then this is just a linear combination of the columns of PL minus 1, and we're going to set that equal to 0. So what are we usually looking for when we're setting a linear combination equal to 0? We're looking for the fact that, well, maybe this can't be, maybe this is a trivial linear combination, or maybe we can find a non-trivial combination. If we can only find the trivial combination, or if only the trivial combination works, then we know that the columns of PL minus 1 are all linearly independent. All right, we're going to use some information that we gleaned from the last couple of results. All right, so we know that this is just the vector representation, the coordinate vector of this this function, but in the new basis, right? So these are the coordinate vectors for some underlying functions VL minus 1 in these two separate bases, BL minus 1 and BL, respectively. So what do we know? That the only way that this vector can be equal to 0 is if this function is equal to 0, right? Whether it's expressed in this function space or the function space VL. The only way that this can be equal to 0 is if all of its coordinates are equal to 0. Okay, so the only way that VL is equal to 0 is if VL minus 1 is identically equal to 0 in that space. But if that's the case, then it must be that the coordinates in the original basis, BL minus 1, must be 0 also. But this says that the only expression, or the only way that we can express 0 using this linear combination, is the trivial linear combination. All right, so that says that the columns of PL minus 1 have to be linearly independent. But that also tells us that the rank of PL minus 1 has to be equal to its number of columns. So we're done. And of course, the reason why the rank of R is the same is because that's just the transpose of P. So the rank doesn't change when we take transposition. All right, I'm going to pause there and take any questions you guys might have. It's good little place to take a break. You can turn your cameras back on. So before we get into talking about the stiffness matrices, any questions about these spaces? All right, so the next topic that we want to talk about in this chapter on the finite element method is the stiffness matrix. We saw how to do this, or in other words, we saw how to construct or compute the stiffness matrix in chapter 3, and the methodology is going to be more or less the same here and going forward. All right, we'll just dive right into it. Now we've already defined this thing, this object we call little a, this bilinear form. So here we go. Suppose that VL and TL are defined as above. We're going to define the stiffness matrices AL in RNL and L via this prescription for all I and J between 1 and NL. So all you do is, if you want to find the IJ entry of the AL stiffness matrix, you're just going to plug in the two basis functions. You're going to plug in the basis function psi LJ, but you're going to put that in the first position. J goes in the first position, and I goes in the second position, psi Li. Okay, so I and J, this ordering gets screwed up. And it doesn't matter much at all because this is a symmetric bilinear form. So then we can reverse them back. But sometimes bilinear forms are not symmetric, and that's why it's important to keep this prescription. I'm not going to show you any examples of that style or that case, but it does happen where these bilinear forms are not symmetric, and so this ordering is important. So this is the energy inner product, or the A bilinear form that we introduced very early on in this chapter. Let me remind you what it is. So AUL, or UV, is equal to the L2 inner product of the gradient of U against the gradient of V. Now I should probably say something about this for a second. This really makes sense only in 2 and 3D. If it's 1D, then we're just going to replace this by its first derivatives. I should say something about this object here. So what does that mean? Okay, so this means, by definition, so this is the integral from from over omega, not 0 to something, but just over omega of grad u dot grad v. Okay, so grad u is the nabla operator acting on u, and that gives a vector. And this is also a vector, so we dot them together. Those are two vectors that gives a scalar once we do the dot product. And so once we do the dot product, we can then integrate this in the ordinary sense because this is just a function. So this is how we define this object. This is what we call the energy inner product or the A inner product. That was defined in equation 2. Now, to move forward, to prove there are a couple things we want to prove about the stiffness matrix. One is obviously that it's symmetric. The other one is something that we're commonly needing, and that is we want to prove that this family of stiffness matrices is positive definite. So symmetric, positive definite. The other thing we want to show, if at all possible, is that the way we've defined this family of stiffness matrices shows that they satisfy the Galerkin condition. So that's the third thing we want to solve. To do the positive definiteness, we need to establish, or we need to have this object called the Poincare inequality. So here's where we can start being a little bit general. Suppose that D is equal to 1, 2, or 3. Omega is an open polygonal, or by, I guess, polygonal in higher dimensions, we need polyhedral. So this is just a generalization of that. Polygonal polyhedral domain. Then there exists a constant CP greater than or equal to 0, depending only on the structure of the domain, such that CP times the norm of V in the L2 norm squared is less than or equal to the energy inner product of V against itself. Okay, so this is just the usual L2 norm over omega. We're going to square that. So just in case you've forgotten, if I want to compute the L2 norm of a function, then that's the square root of the integral over omega of V times itself, not the dot product here, but just V times itself, or in other words, V squared. That's less than the A inner product of V against itself or acting on itself. And this holds true for any V whatsoever in H01. This is called the Poincare inequality, or equations like it are called Poincare inequalities. We're going to write this so that the Poincare constant sets over on the left. You can also bring it over to the right. You can also write the Poincare inequality without the square. And of course, all those things are entirely equivalent to what we have here. It's just that the constant, depending on where you put it, whether it has a square or a square root, um, is just up to you. You get to decide how you want to define that constant. We just know that it exists, and so in 571, I often asked my students, that is in classical numerical analysis, to show that a Poincare inequality holds over the unit interval in one dimension, and the Poincare constant comes out to be just 1 in that case, no matter how you slice it. Okay, so that we need the Poincare inequality. And that's going to allow us to prove a couple of things. First of all, the stiffness matrices that we just created are all going to be symmetric positive definite. Moreover, they're going to satisfy the Galerkin condition, assumption G0. That is, each AL minus 1 satisfies the wrap condition. RL minus 1 times AL times PL minus 1 is equal to that matrix, AL minus 1. This holds for all L between 1 and capital L. You can't go down to 0 because if our index is 0, then we're talking about minus matrices of minus index, which don't make any sense. All right, so we have 3 steps to prove: symmetry, positivity, and then the Galerkin condition. So let's try symmetry first. Symmetry is quite easy, actually. It follows just by the definition. So ALIJ, that's by definition just this, but this bilinear form is symmetric. It doesn't matter where we put the basis functions, they can be interchanged. And so once we get to this stage, we see that that's just ALJI. So we can freely interchange the I and J coordinates, no problem. So that proves symmetry. What about positivity? Positivity, we have to show that anytime we do a computation like that, VL transpose AL VL, we get something which is strictly greater than 0. But let's not worry about that for a moment. Suppose that we just have an arbitrary VL. All right, so that's a vector. If that's arbitrary, then that has associated to it something more or less arbitrary in VL. That's the finite element function that such that the coordinate vector for that finite element function is just this bold VL. Okay, so this finite element function has some coordinate vector, and we've decided to make the coordinate vector arbitrary, but that somehow confers some arbitrary nature to this finite element function VL. All right. And there's only one function. It has to be unique because of the uniqueness of basis representations of functions that have that coordinate representation VL. Now, using the Poincare inequality, we use Poincare with respect to VL, right? Because Poincare was something that we found for functions, and they hold for all V in H0 minus 1. Well, our finite element functions are going to be functions from some sort of finite dimensional subspace of this set. So the Poincare inequality will still hold for our finite element functions. So that's what we have written here. If it's a finite element function, then the Poincare inequality holds. So we have some CP for which that holds. Now, we know that the basis representations or the coordinate vectors for these guys in the basis representations in BL are just given by these vectors bold VL, right? And so that's this expression here. It just has some unique basis representation. Now, A is a bilinear form, so it's linear in both the first and the second components. So I can use the linearity to pull these summations out, and in fact, I can pull the coefficients out as well, right? So I have this object here in the end. But this object, if it doesn't take too much figuring to see this, is exactly equal to VL transpose AL VL. It's just equal to this quadratic form. Okay, this is equal to that. Just a very simple calculation shows that. Now, here's where we get positivity. We already know symmetry. We get positivity from the fact that this is greater than or equal to this function here, okay, or this functional norm. This guy is equal to 0 if and only if it's the 0 function in L2. That says that the only way that this thing can be equal to 0 is if the function is function VL0, but that means that the coordinate representation or the coordinate vector would have to also be exactly equal to 0. All right, so this says this is equal to 0 only if VL, the coordinate representation, the coordinate vector VL is equal to 0 itself. Otherwise, it's greater than or equal to 0. And then this, of course, means that the matrix that we wanted is positive definite. So that's the positivity. So we have symmetry and positivity. Now we only need the Galerkin condition. So remember, the way we define the stiffness matrices, we define them all at once via that condition. And so AL minus 1 is already defined. So now we only have to show that AL minus 1, defined as it was, satisfies the wrap condition. So let's use the definition of AL minus 1. So we put in this basis vector, or this basis function, and this basis function into the A inner product, the energy inner product. Now we use the fact that these have unique basis representations in BL. And of course, the coefficients in those basis representations just involve these things called the elements of the prolongation matrix. That's how we define the elements of the prolongation matrix, in fact. All right, so now we can use the linearity here and in the second component, pull those sums out, pull the coefficients out, and then all that we'll be left with is A acting on these two basis elements. But notice now the basis elements are not at level L minus 1 as they were before. They're now at level L because we've rewritten our basis representations of these functions in the finer level basis BL. All right, now just a couple of steps here. All we're doing is rearranging terms, flipping signs, etc. And we're going to show that actually what we have when we get to this stage is just a multiplication of three matrices. So notice we have two free parameters here, I and J. I and J. So what we still have to have two free parameters over here. And there are still two free, I and J. These S and T parameters are summation parameters and they completely go away. Now we lastly notice that what these matrices are here are just the restriction, fine level stiffness matrix, and the prolongation matrices. And so AL minus 1, we've shown that this, by the way, I guess the one final step could be in order. Could say RL minus 1, AL, PL minus 1, IJ. So that's just the IJ entry of this matrix. Okay, so this whole thing is just the IJ entry of that matrix. But that says that the two elements that we're comparing, if the IJ entries match up, then the matrices must be the same inside those brackets. So AL minus 1 equals RL minus 1, AL PL minus 1. AL minus 1, in other words, satisfies the wrap condition, also known as the Galerkin condition, and we are done. So let's see. Is there a typo in the subscript PL minus 1? Shouldn't it be S and J? So this is a question in the chat. So S and J rather than J and S, I guess. Should it not be S and J? Let's see. Let's go back to those definitions in 4. So first we have psi L minus 1J and L minus 1I. We're going to use the summation indices variously as S and T. All right, so we want to know, is this, are these coefficient orders correct? Okay, so I'm going to go back and check. Oh, come on, let me go back. Summation, it's the second index. Yeah, I think that looks okay to me. See if I can get back to the right page. I think so. So that one looks okay. L minus 1 SJ S and TI T. I think so, but I could be. Okay, so let's see, make sure that we did when we pulled these things out. Can rearrange that all I want. J T I. So this one now I'm going to take a effectively use a transpose. That is, oh, this one here. I think that's what you're asking. I think this here, right? I got the order of that one wrong. Okay. I think that's so reversed order. I think that's the typo. Okay. Yeah, thanks for catching that. All right. So that's just the Galerkin condition, and I wanted to make a remark. I said before that you can show that the prolongation and restriction matrices are full rank. This last calculation shows that as well. It shows that they're full rank. We know that AL minus 1 is positive definite because the proof that we have here is level independent. All right. So this applies also for AL minus 1. So AL minus 1 has to be symmetric positive definite, as does AL. Well, if it really satisfies the wrap condition, the only way that's possible that I could satisfy the wrap condition is if these two matrices here, or the only way I could satisfy the Galerkin condition and have these two matrices both be symmetric positive definite is if these pre-multiplier and post-multiplier matrices are also full rank. And so that holds. Okay, so that's another proof that PL minus 1 and RL minus 1 are a full rank. Otherwise, AL minus 1 could not be positive definite. The best we could say about it is that it would be positive semi-definite. All right, so that's some facts about the stiffness matrices out of the way. Just to remind you of some other quite usual definitions that we're going to use. So we need the Euclidean inner product on level L. So that's just the standard Euclidean inner product. Or in other words, it's VL transpose times UL. The norm, the Euclidean norm on level L is you just take this inner product of a function with itself and then take the square root, you get the norm. The stiffness matrix, or each stiffness matrix, because it's a symmetric positive definite matrix, induces an inner product called the energy inner product, or the AL inner product, and it does that in the usual way. So these are all just recalling things that we've done many, many times. And of course, we can create an energy norm by using the energy inner product. You just take the same function against itself in the energy inner product, and then you take the square root. So all those are things that we're quite familiar with by now. Now, we want to nail down the size of the condition number as precisely as we possibly can. To do this, we need some estimates. Now, in chapter 3, we were able to nail down the our spectral radius and our condition number very precisely, and that's because we were using a uniform mesh in one space dimension. We had control over all the parameters essentially. We knew a lot of information, and therefore we could calculate the condition number and the spectral radius uh, to any precision we wanted to, essentially. We had formulas for those. So now, when we're dealing with meshes that are no longer have this nice structure as we did in chapter 3. Chapter 3, we were just in one dimension with a uniform mesh. Here, if we're in 2 dimensions or 3 dimensions or whatever, we may not have any kind of uniformity in our mesh structure, but are we still able to predict the size of the condition number? It turns out yes, and we can do this with some interesting tools. All right, so the following results can be found in any good finite element books, I've asked you when the time comes to do these computations in 1D to see how they go, but otherwise, I'm not going to ask you to do them in 2D or 3D. So suppose that D is any dimension that we might be interested in, 1 through 3, and we have any level of interest, and VL coming from capital VL arbitrary. Let's, as usual, assume that capital or boldface VL is its unique coordinate vector in this basis BL. Then there are always constants, C2 and C1, both independent of L and VL, such that we have this norm equivalence statement. So this says that the L2 norm of the function VL is equivalent to, in some sense, the vector norm of its coordinate representation using the Euclidean norm. Now we could write these with just generic constants, but in this case, we know how these constants depend on L and on the dimension. They depend on L in the following way. Well, there's a constant which is independent of L and the dimension and independent of the function, but then we can also capture this part of the constant where we have this dimensional dependence and this L dependence. It's precisely HL to the D power here and here. Okay, so where does this come from? So notice that VL is a finite dimensional space and RNL, so we can think about it like this. VL is connected to RNL. And it's connected via the basis representation of the basis VL. Because any function we take that lives over here that we call VL without any arrow or bold facing has a unique representative over in this space that is just some vector. And they're connected through this basis representation. So there's a one-to-one mapping between these functions. So we can identify these two spaces with each other. Okay, this is space identification. They're really just the same spaces. Of course, over here we use, well, these are just vectors, they're coordinates, but over here these are actual functions. Now, all we're saying here is that these two norms on these objects are equivalent. And this is always true. In finite dimensions, any two norms that you can produce on a space are equivalent to each other, right? So we've seen this many times in numerical analysis. If we take the L1 norm, I'll call it the little L1 norm, this is equivalent to the Euclidean norm, little L2, right? And that means that there's constants C1 and C2, one bigger than the other. All right, so this notation is a little bit confusing because this doesn't mean, I guess what I would usually write is, so forget what we are doing in this chapter or in this book, but usually we call the one norm, that is just the non-Euclidean norm, and the two norm is labeled 2, that's the Euclidean norm, and this is a 1 norm. Or we could have infinity norm here, right? That might be a little less confusing. Okay, the max norm. But in any case, we know that all vector norms on Rn are equivalent to each other. But what you may not understand or may not have heard before is that on a finite dimensional space, all norms are equivalent, no matter what that space is. Now, the fact that these two spaces are isomorphic to each other means that we can make this statement across these two spaces. In other words, we can use a measure of norm in this space, and it's going to be equivalent to the measure of a norm in this space. So this is just norm equivalence kind of hiding in a slightly different form. So I'm not going to prove this. Again, this scaling here shows where the level dependence and the dimension dependence comes in. And I'm only going to ask that you prove this in a homework for the case where D is equal to 1. So in that case, then it's a nice simple picture that you can draw out, and you can think about, well, what does this image look like? What is the L2 norm really saying? And then what is this norm saying? When this is the coordinate vector. You can show in the one dimension pretty easily that you have this norm equivalence and you get this level and dimension dependence. So in one space dimension, of course, D is just going to be equal to 1. Okay, so this is what we call norm equivalence. The next thing that we want to use is what's called an inverse inequality. So the previous was called a norm equivalence. This is what's called an inverse inequality. Now, let me explain a second. So I'll first give the result, and then I'll come back and tell you what this inverse inequality really says. So suppose that D is equal to 1, 2, or 3. L is any level between 0 and L inclusive. There is a constant C3 independent of L, such that if I take the energy inner product of VL against itself, that's less than that constant C3 times HL to the minus 2 power times the L2 norm of VL squared. Why is this so? Well, first of all, this is a typo here. Should be a comma. This holds for any VL in the finite dimensional space. So the first thing to keep in mind is that this only holds on finite dimensional spaces, okay? It doesn't hold if I say that V is equal to this infinite or some function from this infinite dimensional space. Then this result is no longer going to make sense. It's no longer going to hold. Now, why does this result hold? So this is something that you can also prove fairly straightforwardly in 1D. It's not so easy to do in multiple space dimensions, but it's not impossible either. 1D is not too bad. This object over here is the square of a norm. The energy inner product gives rise to a norm, and it's the same reason that the stiffness matrix is symmetric positive definite. It's related to that. The energy inner product gives rise to a norm on this space VL. Remember I said that all norms on a finite dimensional space are equivalent. This is also a norm on that space VL. Well, if all norms are equivalent, then there has to be some constant of equivalence relating these two norm objects together. Actually, these are the squares of norms here. These are the squares of norms, but it doesn't matter. We could take the square root and the result still holds, but with a slightly different C. So this is just a statement of norm equivalence on a finite dimensional space. It does not hold on an infinite dimensional space, such as H01. So this is what we call an inverse inequality. Now, what we notice is that you can't beat a derivative norm with an L2 norm with no derivatives unless you pay the price of dividing by factors of HL. So the price of using or saying that a norm with no derivatives is better than a norm or beats a norm with derivatives is I have to pay the price of an HL to some power. So in this case, because I'm trying to beat a norm with first order derivatives with a norm with no derivatives, I have to pay the price of HL to the minus 2 power. That's when I'm squaring both of these. If I take the square root, then it's going to be HL to the minus 1 power. Okay, so if I do a balance like that, trying to beat a norm with derivatives by a norm without derivatives, it can be done, but as long as you're in finite dimensions, because we know that all norms are equivalent in finite dimensions, but the price I have to pay is a constant here. And this constant, it turns out, blows up as L gets larger and larger, right? Because as L gets larger and larger, H gets smaller and smaller. H to the minus 2 power, that blows up to infinity. So you can see why this is not holding in infinite dimensional spaces. That's because VL is finite dimensional space, and we can kind of look at as VL, this is not exactly true, but it's kind of true. It's morally true. As L goes to infinity, this becomes H01. So as we get more and more mesh in there, as the mesh spacing is finer and finer, that's as L gets larger and larger. Basically, we're converging on this finite dimensional space to this infinite dimensional space. Okay, so this is what we call an inverse inequality. Now, as a consequence of 8, the fact that we know we can bound this guy with that, we can replace this here with this vector norm. And so we can show that 9 becomes this object 10. This is still a statement of an inverse inequality. We're trying to beat a norm with derivatives by a norm without derivatives. Okay, and we have to pay the price of some constant which may or may not blow up as L goes to infinity. And so this is the constant that can blow up, HL d minus 2. So that's where we're going to end for today with this concept of an inverse inequality. We talk a lot more about this in this course on finite elements. This all flows from this concept of what's called norm equivalence on finite dimensions. But you have to keep in mind that norm equivalence can go weird, can get weird whenever the spaces are growing in size. Okay, so whenever, for example, VL is getting its dimension is getting larger and larger as I take the mesh space finer and finer. That's because it's converging to something which is infinite dimensional, and this object will no longer hold. It's known that this object does not, or this inequality does not hold in this infinite dimensional space. But in every finite dimensional subspace of H01, it does hold. So that's where we'll stop, and I'll take any questions that you guys have.